Okay, so far all we've been doing is called explicit differentiation. What I'm going to show you now is something that we use when it's either very difficult to solve for y in terms of x, or maybe it's impossible to solve for y in terms of x. So let's go ahead and let me show you a couple of functions. I like to show you an example where you can do both methods on, so that you can see that you get the same answers. Now in practical cases, you generally won't be able to do this because the function will not allow you to solve for y, or it'll be difficult to solve for y. But for this function, 3x plus 2y equals 4, I can easily solve it for y. So you can go through the algebra here and solve this for y, and you'll get y equal minus 3 halves x plus 4, and then if you take the derivative of that with respect to x, you'll just get negative 3 halves. And so again, that's explicit differentiation. That's what we've been doing. Now with implicit differentiation, there are some rules I'll show you at the beginning, but basically what it says is you basically hit both sides of the equation with this d over dx operator. In other words, you take the derivative of each term with respect to x. So if I have 3x plus 2y equals 4, then I have to take the derivative of 3x with respect to x, I have to take the derivative of 2y with respect to x, and I have to take the derivative of 4 with respect to x. Well, you know how to take the derivative of 3x with respect to x, that's just 3. And you know how to take the derivative of 4 with respect to x, that's just 0. But here's where it gets tricky. I'm going to take this 2, and I'm going to move the 2 over here, because we can do that with our derivative properties. Now, what is the derivative of y with respect to x? Well, I don't know. I don't know what the derivative of y, because I don't know what y is. So all I know is that y is some function of x. So in that case, all I can say is the derivative of y with respect to x is just that, the derivative of y with respect to x. So I have to write it like this. Now, you can actually move the 3 over to the other side now and isolate this term. So you'll get 2 times dy over dx equals negative 3. And then divide both sides by 2, and you'll get dy over dx is equal to negative 3 halves. And that's exactly what we got when we did it explicitly. Let me show you another one. How about xy equals 5? Well, if you can easily solve that for y, that's just y equals 5 over x, or 5 times x to the negative 1. And then you can apply your basic rules for differentiation to this to get that the derivative of 5x to the negative 1 is actually minus 5x to the negative 2, which is minus 5 over x squared. Okay, so there's the derivative using explicit differentiation. Now let's do implicit differentiation. So with implicit differentiation, I've got to take the derivative of xy with respect to x, and I got to take the derivative of 5 with respect to x. Well, the derivative of xy with respect to x, remember x times y is a product, and I don't know what y is. Y is just some function of x. So I've got to treat it as if I don't know what it is. So I'm going to have to use the product rule. So I'm going to take x times the derivative of y with respect to x, because remember I don't know what the derivative of y is, so I just have to state it like that. And then I do the other half of the product rule. I have y times the derivative of x with respect to x. And actually this is just 1. So that's just y times 1. I'm not sure why I didn't just say 1 there. So anyway, y times 1. Now, if I move this y over here, I can move this y over here, and then that'll leave me with x times dy over dx equals minus y. And then that gives me the derivative of y with respect to x. It's just minus y over x. Now, you might remember before we found that this was actually minus 5 over x squared. And so you may say, well, that doesn't look like the same thing. Well, it may not look like it, but we can kind of cheat in this case. If you go back up here, remember y was equal to 5 over x. Now normally you wouldn't know that. But in this case, we do know that y is equal to 5 over x. So I actually can take this derivative And if you replace the y with 5 over x, you get minus 5 over x divided by x. And you can easily show that that's the same as minus 5 over x squared. Now again, like I said, we generally can't show that. On these other examples, we won't be able to do that because we can't solve for y. All right, let's take a look at this example. All right, so I'm just going to tell you the steps you're supposed to do rather than scroll back up there. What you're supposed to do on implicit differentiation is the first step you do is you take the derivative of each term with respect to x. So notice I have 1, 2, 3, 4 terms here. So each one of these, I'm going to take the derivative with respect to x. Now, x squared y is a product, so I have to use the product rule. So I take x squared times the derivative of y with respect to x. Well, as I said before, the derivative of y with respect to x is just that, dy over dx. And then I still got to do the other half of the product rule, where I say y times the derivative of x squared with respect to x. Well, when you're taking the derivative of a function of x with respect to x, that's explicitly. So I can actually take the derivative of this and get 2x. So that's just going to be 2x times y, and that's right there. And then here, the derivative of minus 5x with respect to x is just minus 5. And again, the derivative of y with respect to x is what? The derivative of y with respect to x. And the derivative constant's always 0. Okay, so now all I did in this next step was just rewrite this as 2xy. Now notice here, this has a dy over dx in it, and this has a dy over dx in it. So the steps tell you to get all terms that have a dy over dx in it as a factor to the same side. So I'm going to keep these two terms on the left. And then I'm going to get the other two terms and move them to the right. So the 2xy, I move over here and it becomes minus 2xy. And the minus 5, I move across the equal sign, it becomes plus 5. What that allows me to do is that allows me to take these two terms and factor out the dy over dx. So if I factor the dy over dx out of this term, I get x squared. And if I factor it out of the second term, I just get 1. And now, if I divide both sides by x squared plus 1, I get that dy over dx, the derivative of y with respect to x, is 5 minus 2xy over x squared plus 1. Now, one of the problems that you're going to run into with implicit differentiation is your derivative many times is going to be written not just as a function of x, like it was with explicit differentiation, but it will be written as a function of x and y. So what that means is if you want to use this derivative to find the slope or the equation of some tangent line, you're going to have to not only know the x value, but you're going to have to also know the corresponding y value in most cases. All right, let's take a look at another one. Here's one with 3 terms. So again, I'm going to take the derivative of each term with respect to x. So right there. Now I guess you could skip this step and just go straight to it. But let's see, the derivative of xy, I got to use the product rule. Now, instead of using dy over dx here, I'm going to shorten it a little bit and I'm going to use y prime in its place. It's okay to do that as long as you know what y prime represents. And in this case, it represents dy over dx. So this would be x, using the product rule, I'd get x times the derivative of y with respect to x, which is just y prime, then plus y times the derivative of x with respect to x, which is 1, so that's just going to be y times 1 for the second half of the product rule. Now, remember when you have a function to a power, you have to use the general power rule, and y is a function of x. I don't know what it is, but it's some function of x. So I have to use the general power rule. And remember, the general power rule says you use the power rule, so that would be 3y squared, but then you multiply by the derivative of the inside. So I have to multiply by the derivative of y, which is y prime. And then the derivative of the constant is 0. So now I have 2 terms with y prime in there, so I'm going to keep those on the left. And then the term without the y prime, which is y, I move it to the other side, and it becomes a minus y. Then factor the y prime out of these 2 terms, and I get y prime times x minus 3y squared. And then now I can divide minus y by x minus 3y squared to isolate y prime. Now, if you don't like this negative, what you could do, and this is not something you have to do, but if you multiply the top and bottom of this fraction by -1, it actually will change all the signs, and the numerator wouldn't be negative. I'm just showing you that there's another way to write the answer is all I'm doing. Okay, now let's take a look at this one. This one I have x cubed minus 2xy equals 3x. And I'm going to apply d over dx to each term. This one is explicitly differentiating. So explicitly differentiating x cubed gives me 3x squared. Now, what I'm going to do here is I'm going to just move this 2 out here and then just take the derivative of xy. Well, that means the product rule, so we've done that a couple times already. So that's going to be x y prime plus y. And then the derivative of 3x with respect to x is 3. So now I'm going to distribute the -2 here, and I'll get -2xy prime minus 2y. Now I only have one term with a y prime in it, so I'll just leave that over here. And I'll move all the other terms to the other side. So the 3 was already there. If I move the -2y there, that'll make it a plus 2y. If I move the 3x squared over there, that'll make it a minus 3x squared. So now all I have to do to solve for y prime is divide both sides by -2x. So again, there's the answer, 3 plus 2y minus 3x squared all over -2x. And again, if you want to multiply the top and bottom by -1 and get a different looking answer, I mean, you could do that. I only do that in case you're looking at answers in a book or something and you think you got the wrong answer because your answer doesn't look like the one that's in the answer sheet. All right, I'm going to hold off on number 3. I want to go ahead and go to number 4. Number 4 says find the slope and the equation of the tangent line at the point 9/2, 2 for this graph. Well, first of all, let me just let you know that I gave you both an x and y value here. And if you actually plug this x and y value into this equation, you'll see it gives you a true statement. So the point 9/2, 2 is on this graph. Now, I know from up here I actually found the derivative was y over 3y squared minus x. So all I have to do to find the slope of the tangent line is plug 9/2 and 2 in there. So plug 9/2 in for x and 2 in for y. So I'll plug a 2 in here and here and a 9/2 in here. And then I'll get 2 over 3 times 4, which is 12 minus 9/2. So that gives me 12 minus 9/2 is 15/2. So I have 2 divided by 15/2, which is 4/15. Now, 4/15 is the slope. I know the point is 9/2 2, so now I can get the equation, use the point slope form. So take y minus 2 equals 4/15 times x minus 9/2, and then distribute that, and you get 4/15 x minus 6/5, then add 2, and you get 4/15 x plus 4/5 for the tangent line. Now, what I'd like for you to do is go ahead and graph this function on a utility, and then graph this tangent line, and notice that I think it'll look kind of like this, and then the point will be maybe right here. And when you graph the tangent line, you'll actually see the tangent line go through there like that. And so that it's kind of neat to see that. Now, I've got some more examples I want to show you, but we're going to wait until the next video. And I'll do some more examples of implicit differentiation on the next video.